Hey guys, welcome to another Algebra 2A video. This time we're talking lesson 1-3, square roots. Square roots are, again, something you probably should have learned back in algebra. You definitely dealt with them in geometry with things like Pythagorean theorem and special triangles, stuff like that. What is a square root? Well, I like this example here because this is really cool. The largest mosaic in the world is located on the exterior walls of the Central Library of Universidad Nacional Autónoma de Mexico in Mexico City. I'm sure I'm butchering that Spanish, but whatever. It covers an area of 4,000 square meters. If it were laid out as a square, you could use a square root to find its dimensions because square roots are the opposite of squares. And you're actually going to do that in lesson exercise number 42 in your homework tonight. So pretty cool. The side length of a square is the square root of its area. This relationship is shown by this guy here, the radical symbol. The number or the expression that's underneath that radical symbol is called the radicand. And the radical symbol indicates only the positive square root of a number, called the principal root. So when you do the square root on your calculator, you're always going to get the positive answer. But there could be negative answer as well, because, and we'll get to that in just a second, but negative square root of a number can be used, and we also use the plus or minus sign to indicate both roots, not just the principal, but also the negative. Why do we have to worry about a negative? Well, think about it. 25, square root of that is 5, because 5 squared is 25. Now, if I have negative square root of 25, that means I'm going to have negative 5. If I have plus or minus the square root of 25, that means I have plus or minus 5. It could be 5 or it could be negative 5. Because if I take negative 5 and I square that, remember, two negatives make a positive. So there is actually two solutions to every square root equation or square root operation. But we really only worry about the principal roots. Now, what are these perfect square numbers like 5? 25 is a perfect square because it has an integer solution when you take the square root. Because 5 times 5 is 25, so you undo it, you get 5. So let's go to our note sheet here, and I've written down here all the perfect squares from 1 to 200. I wrote them down already because it would take too long to just write them all out. But basically we got 1 squared is 1, 2 squared is 4, we got 9. Let's highlight them. Yeah, come on. 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. And we could keep going if you want. Heck, 16 squared is 256. How about that? I have these all listed on the backboard in the classroom, but you probably should put these in your notes somewhere so that you have them because you're going to be using them today. Now, if we go back to the text, one of the things you can do is you can estimate the value of a square root of a number that's not perfect by figuring out where it lies in between perfect squares. So like the square root of 5 lies between the square root of 4 and the square root of 9. So the answer to the square root of 5 is going to be somewhere between 2 and 3 because the square root of 4 is 2 and the square root of 9 is 3. Probably be closer to 2 than it would be to 3, but that's just the way this works out. So like if I wanted to estimate where the square root of 34 lies, well, that's right between 25 and 36. It's actually much closer to 36. So the square root of 34 is going to be between 5 and 6. So you can try some decimals and try to figure it out. Looks like 5.8 squared is 33.6. 5.9 squared, that's too much. It's 34.8, so we can't go over. Looks like the Price is Right, right? Closest to the answer without going over wins the prize. So they say probably closer to 5.8. And in fact, if you actually evaluate it on a calculator, you will get 5.83. 0195, so on. And remember, that decimal is going to keep going forever because it's an irrational number. We talked about that in lesson 1. But 5.83 seems like a pretty good estimate. Now, there are properties of square roots that will allow us to simplify them. We want to make our square roots as simple as possible. And to simplify a square root means you want the smallest possible value left inside the radical symbol, the smallest possible radicand. So what we're going to do here is we're going to use the quotient and product properties. They're also written on your note sheet, but they're right here. The square root of a product is equal to the product of the square roots of the factors. So the square root of AB is equal to the square root of A times the square root of B. And it works the other way too. If I have the square root of A times the square root of B, so if I have two square roots and I'm multiplying them together, I can take the square root of the product. So how do I use this? Well, if I have something like the square root of 12, 12 is not a perfect square. However, it has a perfect square factor in it, 4. 4 is perfect, it's on our list. 4 times 3. So I could break this up into 4 times 3, and the square root of 4 is 2. Square root of 3, can't do anything with it, so I get 2 times the square root of 3. Now, like I said, it goes the other way too. If I have the square root of 8 times the square root of 2, neither one of those are perfect squares, but they're both square roots, so I can multiply them together. And so 8 times 2 is 16. So the square root of 8 times the square root of 2 is the square root of 16, which becomes 4. The same works for quotients. If I have a fraction or a division problem and I'm taking the square root of it, I can square root the numerator, square root the denominator to simplify. And I can go the other way too. If I have a square root divided by a square root, I can make it a single radical and use that to simplify the radicand and possibly get rid of the square root altogether. These are written here in your note sheet. And these examples here are pretty good to follow. Like I said, it works both ways. If you identify your perfect squares, you can use them to simplify square roots. So like 100 is the perfect square because 100 is a perfect square because 10 squared is 100. Also, negative 10 squared is 100, like I said. But if we have like this, the square root is 72, we're going to look for that perfect square factor. That's what we want to do. Look for the perfect square factor in 72. And you want to go big or go home. You want the biggest one possible. Go big. Go home. We want the greatest common factor. So 36 times 2 is 72. And square root of 36 is 6. So we get 6 times the square root of 2. Here we have the square root of 64 25ths. We can break it up. Square root of 64 divided by the square root of 5. That becomes 8 over 5. Because they're both perfect squares. This works the other way too. You can multiply the square roots together to simplify them. You can divide square roots to simplify them. All right. Excuse me. So let's do some estimating. Looking at our list, we got the square root of 78. Excuse me. 78 is between 64 and 81. So I'm going to say this. Square root of 64 is less than the square root of 78, which is less than the square root of 81. So we're going to be somewhere between 8 and 9. Now, 78's closer to 81 than it is to 79, so let's see. Let's try 8.8 squared, 77.4. 8.9 squared is 79.2. So let's see. So 8.8 squared is 77.44. 8.9 squared is 79.21. So that's not going to work. So it's about 8.8. That is estimating. 57. That's going to be between 64, and 49. And again, I'm picking these values because they are perfect squares. So we're between 7 and 8. It's a little closer to 64, so let's try 7.6. 7.6 squared. Actually 7.6 squared is too high. 7.6 squared is 57.76. So let's try 7.5 squared. We get 56.25. So actually that one is probably a little bit better. But that's basically the idea. This estimating stuff, we're not going to do too much of it. It's just to kind of give you an idea of where these things lie in terms of their values on a number line. What's more important is this stuff here, the simplifying the square roots. So let's see, 243. 243 is not a perfect square. And it's not because if I go back up here and look at it, we go from 225 to 256. So 243, not perfect. But does it have a perfect square factor? So I'm going to just start trying some perfect squares. 243 divided by 49 is equal to, no, 243 is not divisible by 49. 243 divided by 9 is 27. 243 divided by 81 is 3. All right, so 9 works. 9 is a perfect square that goes into 243, but it's not the biggest one. So I'm going to make this 81 times 3. So what this ends up being is the square root of 81 times the square root of 3. That is 9 times the square root of 3. That's it. You look for the biggest value, greatest common factor. Number 5, I'm going to make this a single radical. Now here's the thing. These guys will cancel out. So I get the square root of 9 divided by square root of 4. Square root of 9 is 3. Square root of 4 is 2. There it is. So the square root of 90 divided by the square root of 40 is 3 halves. 42 times 3. These are not perfect squares, but they are both square roots. So I can make it a single radical. And then I get the square root of 126. I guess that's it. Now maybe 126 has a perfect square in it. Let's see, divide that by 3. No, wait, that's what I just did. Divide it by 16. No. Divide it by... No. Wow. Divided by 9. Nope. Oh, yeah. All right, so 9 times 14 is 226, so we get 3 square roots of 14. I don't know. That one was weird. Took a while too. Let's do some more. Negative 4 divided by the square root of 144. Well, this is like negative 4 divided by 12 because the square root of 144 is perfect. That would be negative 1/3. 125 divided by 5. That one is actually in your textbook. This is going to be the square root of 25, which is 5. Negative square root of 320. All right, so I'm going to make this 320 is got to be a perfect square. Now I know 10 goes in there, but that's not perfect. Let's see, 320 divided by 16. That might work. 16 times 20 works, and 16 is a perfect square, but I think I can go bigger. 320 divided by 64 is 5. 64 64 times 5. So I'm going to make this 64 times 5. That's going to be negative 8 square roots of 5. So you want the biggest guy in that denominator. All right. The next concept is what we call rationalizing our denominators. And to do that, I'm going to go back to the textbook here, and I'm going to show you how this works. If a fraction has a denominator that's a square root, you can simplify it by what we call rationalizing the denominator. We do not like to divide by radicals, because when you're dividing by any irrational number, and it just doesn't work. So what we want to do is we're going to multiply both the numerator and the denominator by a number that creates a perfect square in the denominator, so we don't have a radical anymore. So let me show you these examples, and then we'll do some on the note sheet. So square root of 2 square roots of 2 divided by the square root of 3. I could make this a single radical, but 2 divided by 3 doesn't simplify. So what I'm going to do is I'm going to multiply the top and the bottom by the square root of 3. So up top we get 2 times 3, the square root of 6. The bottom, the radical cancels out because you get 3 times 3, which is 9, and the square root of 9 is 3. So this becomes our answer, 2 square roots of 6 divided by 3. Not necessarily a simpler looking problem, but definitely one that we can work with because we don't have the radical in the denominator. Here we got square root of 8 divided by the square root of 18. All right, so they said multiply the top and the bottom by 2 because 18 times 2 is 36. So what we get in the bottom is 6, and then the top we get 8 times 2, 16. Oh, square root of 16, that's 4. So 4 over 6 becomes 2 over 3. So it ends up being that when we rationalize, we can get rid of the radicals altogether. So let's take a look at this. Number 10. Let's change the colors just for fun. All right, so I'm going to multiply the top and the bottom by the square root of 5. When you have a single radical like that, that's pretty much all you can do. Up top, I'm going to get 6 times the square root of 5. Simple. The bottom, the radicals are going to cancel. I'm just going to get 5. Here, number 11, multiply the top and the bottom by the square root of 3. And let's see, so I'm going to get negative 3 times the square root of 45 in the top, because 15 times 3 is 45. In the bottom, I just get 3. These guys are going to cancel. So I get negative square root of 45. Now, you might not know this right away, but after you've done some of these assignments in your homework, you're going to realize that 45 has a perfect square in it. It has 9. 9 times 5. So I end up with the square root of 3, negative square root of 3. No, I'm sorry. 3 times the square root of 40. Let's just start all over. So 45 is 9 times 5. Square root of 9 is 3, so we get negative 3, square root of 5. Wow. All right. Number 12. We have this square root of 6 down there, so I'm going to multiply the top and the bottom by the square root of 6. 13 times 6. I don't know if that does anything. It's 78. Square root of 78. That's it. At the bottom, though, I'm going to get 4 times 6. So I get the square root of 78 divided by 24. And I don't think 78 is a perfect square. It certainly isn't. I don't think it has a perfect square factor. No, 4 doesn't go in there. 9 doesn't go in there. 16 doesn't go in there. 36 doesn't go in there. It's not going to work. So that's it. You're done. Sometimes you can't simplify. All right, moving on. We also have this concept of what we call like radicals. Like radicals have the same radicand, like square root of 2 and 3 square roots of 2. Negative 6 square root of 15 and 7 square root of 15, square root of a b squared, and 4 square roots of ab squared. Unlikes have different radicands, so the square root of 5, square root of 2. They're both square roots, but they're not like. X and 3x, not like. Xy squared, x squared y, they're not like. If square roots have the same radicand, square roots that have the same radicand called like radical terms, and you can add and subtract square roots. You might have to simplify first, but then you can just combine your like radical terms. So sometimes it's simple. Like here in number 13, we have 7 square roots of 5 minus 10 square roots of 5. That's just going to be negative 3 square roots of 5. You're going to treat it just like a variable because remember that 7x minus 10x is negative 3x, right? Combine like terms, so we're going to do the same thing with our radicals. The problem is, sometimes they don't appear to be the same. 3 and 12, those are not like radicands. So you would think, oh, we can't do anything. However, we can simplify the square root of 12. In fact, we looked at an example like that earlier. This is going to be 3 times square root of 4 times 3, so we get 12 square roots of 3 plus 3 times 2 square roots of 3. So we get 12 square roots of 3 plus 6 square roots of 3. And now they're the same. And 12 and 6 is 18 square roots of 3. So we're going to have to do this for some of these. Try to simplify and see what happens. Number 6, negative 6, that's 20. Square root of 50 is 25 times 2. And then we get plus 4. 32 is 16 times 2. So notice we've got 2 here and here. That's important. So we're going to get negative 6 times 5 square roots of 2 plus 4 times 4 square roots of 2. So we get negative 30 square roots of 2 plus 16 square roots of 2. That's going to be negative 14 square roots of 2. Going to have to play around with some of these. 16, story problems. This is going to be similar to that problem I talked about at the beginning of the book, the beginning of the chapter. Building is a mural painted on an outside wall. The mural is a square with an area of 14,400 square feet. What is the width of the mural? So it's a square, and this is not a perfect square, but the area is 14,400. So a side is going to be the square root of 14,400. Could use my calculator probably to do that. Let's see. Square root of 14,400. And it's even perfect. It's 120. So each side of that building is 120 square feet, or 120 feet. And that's it. Now let's go back to the text, make sure I've covered everything. I think I have. We talked about like terms. And yeah, that's about it. So that does it for today. Don't forget to smash that like button if you learned something. And I will see you in the next one.